Good morning, students. Welcome to chemistry class. Today I am going to the discussing about the structure of atom from the chapter second, structure of atom, particle nature of electromagnetic radiation. Particle nature of electromagnetic radiation. In the previous video, we know the wave nature of electromagnetic radiation. Wave nature of electromagnetic radiation. And now, in this video, particle nature of electromagnetic radiation. Okay, by the Planck's quantum theory. Planck's quantum theory. According to Planck's quantum theory, the body which emit or absorb radiations of all frequencies is called black body. That radiation is called black body radiation. According to Planck's quantum theory, what is the body which is emit or absorb radiations of all frequencies is called black body. That radiation emitted by this body is called black body radiation. The radiations which are emitted by the black body, the radiation is called what? Black body radiation. Okay. Then, and the second part is the exact frequency distribution of the emitted radiation from a black body depends upon its temperature. The exact frequency distribution of emitted radiation. Okay, now emitted radiation. So from a black body, that is depend on temperature. Okay, so which is emitted radiation. Suppose this is one of the black body. Maybe, and after ejection of this any one of the particle that is emitted or absorbed one of the radiations, the radiations distribution of the frequency distribution of the emitted radiation that is depend on the temperature. Its temperature. Okay, now means the frequencies that is depending temperature. So higher temperature, the intensity of the frequency is more, and lower temperature, the intensity of the frequencies is less. Okay, so the exact frequency distribution of the emitted radiation from a black body depends upon its temperature. So that is intensity versus frequency. So frequency is more, intensity also more. Intensity versus from the curve of radiation. So here you will see this intensity and this is wavelength. So at temperature 1 and temperature 2. So what happened? Temperature, the curve, intensity of this curve like this, and second curve is like this. Okay, so at given temperature, intensity of radiation emitted increases. At given temperature, intensity of radiation is increases. With decrease of wavelength, and reaches a maximum value at a given wavelength, and then and then start decreasing with further decrease of wavelength. Further decrease of wavelength. So what happened here? At a given temperature, intensity of at a given temperature, any one of the given temperature, intensity of radiation emitted increases with decrease of wavelength. Increases with decrease of wavelength. Okay, decrease of wavelength reaches a maximum value at a given wavelength. A maximum value at a given wavelength, then starts decreasing with further decrease of wavelength. Further decrease of wavelength means what? First, when at a given temperature, intensity increases when decreasing. This is decreasing order. 1000, 100, 2000, 300. This is nanometer. So minus 19, minus 10 to the power of minus 9. That is the nanometer. So this is wavelength is decreasing here. Wavelength is decreasing order this one. And what happened is, so intensity of the radiations increases at a reaches a maximum position and further decreasing this intensity and further decreasing of the wavelength. So first increases that are getting or reaches at maximum position, and then decreasing further wavelength decreases. So here at temperature 1 like this, and temperature 2 like this, means this is minimum temperature, this is maximum temperature maybe, and here, so that's why T2 greater than T1. So this is higher temperature, this is lower temperature. So at lower temperature, the frequency of the intensity of the frequency of the radiations is low, and higher temperature, intensity of the frequency is high. So that's why this is explained by the quantum. Body which emits or absorbs radiation of all frequencies is called black body. The radiation emitted by this body is called black body radiation. Okay. Next, exact frequency distribution of the emitted radiations, that is intensity versus frequency curve of the radiation from a black body depend upon its temperature. Means temperature increases, frequency also increases. Okay, so like that. And at a given temperature, intensity of radiation emitted increases with the decrease of wavelength, reaches a maximum value at a given wavelength, and then starts decreasing with further decrease of wavelength. Okay, so based on this, he was given some postulates. The postulates are according to plants. He was given some postulates. The postulates is the atoms and molecules. Should emit or absorb energy only in the form of a small discrete quantity. Energy only in small discrete quantity is called quanta or photon. So energy pockets. So that energy pockets are called here quanta or photon. So whatever it may be, the emitted or absorbed radiations that having a small energy discrete pockets. The pockets are called here quanta or photon. So the energy of quanta reaches the energy of quanta of radiation. Energy of quanta of radiation is directly proportional to its frequency. That energy of quanta of radiation directly proportional to its frequency. So and is expressed as E proportional to E directly proportional to nu. E directly proportional to nu. So this is nu. Okay. So this is frequency. This is energy. This is energy. And E equal to h nu. E equal to h nu. Here h is called what? H is called Planck's constant. H is called Planck's constant. E is equal to h nu. E equal to h nu. H equal to where? H equal to Planck's constant. So where the proportionality constant h, that is called what? Planck constant. Planck's constant. Okay. Then and the value is, what is the h value? H value is 6.626 into 10 power 34 joules second. Planck's constant value 6.626 into 10 power minus 34 joules seconds. Okay. Then another one is energy is always emitted. Energy is always emitted in integral multiples of h nu. Integral multiples of h nu. So that's why that is E equal to, we can write E equal to n h nu. N h nu. What is this? N where n is integer. So integers means 1, 2, 3 like that. 1, 2, 3 like that. Okay. So integers. So E equal to h nu. E equal to h nu. So we can any one of the given value will find out by using all the values. Suppose E energy is calculated by using this, when we know this one, and h is or frequency or n, whatever it may be, will calculate by using this formula when knowing when known about another values. Known about another values. Okay. So this is the Planck's proposed the following postulates. What is that? The emitted or absorbed radiation having only small energy pockets. The energy pockets are called quanta or photon. Okay. That energy of quanta directly proportional to its frequency. So that's why you can write E equal to h nu. You can write E equal to h nu. Okay na? So h equal to a proportionality constant h. So that is called Planck's constant. So what is x value? 6.6 into 6.626 into 10 power minus 34 joules second. Okay. So another thing is, you can write also, this is always multiple. Energy is always multiples. So increases. So that's why we can write integral multiples. So we can write that formula equal to E equal to n h nu. N means what? Integer. An integer. Okay. So this is the postulates of Planck's. So this is the Planck's quantum theory. Okay. Thank you for watching this video.